Okay. I came close to forgetting in my other two classes, but somehow I remembered at the last minute and thought, okay, I'll be fine. Narrator, he was not fine. Okay, so those of you who are watching, unfortunately I had not recorded the first few minutes, but this is what has been discussed in those first few minutes. All the information about the midterm. So I will be posting practice test. I'll try to get it up by tomorrow sometime. The practice test will only feature problems of this kind for you to practice on. Again, you're not doing MATLAB on the test. And then practice tests will not include this, but studying the quizzes for these sections to be ready for these questions that will be included on the test. So 15 questions total. And weighted equally. So these sections will be. So these problems will be 10 points each. These will be 5 points each. Okay. All right. And this is the time frame for the test when it happens. So you have a good amount of time, but not a whole lot. Just trying to take into account that, we all have other things to do. All right. Now, okay. As you may have seen, I graded a number of assignments during the over the weekend, some homework ones and quizzes. Although there's been some recent submissions I haven't gotten to yet, but I will very soon. As the assignments come in, I wait until there's a certain critical mass. Like I look at the Canvas dashboard and see what has been turned in. For example, 6 people have turned in the second quiz, so I'll be getting to those soon. But the first priority will be homework 1 and the first quiz. And I want to reiterate something I gave a warning about before, but apparently it bears repeating. The most common way to lose points is when some portion of a question is not done. One example was from the MATLAB tutorial. It was, I think it was the problem 26. I'll just type that in here. So as an example, another equation that was 1 to 26 about Hilbert matrices. So using a MATLAB function Hilb to produce a Hilbert matrix and look at various formats to see the appearance. The last part of the question, we're going to come up with a formula for the entries of the Hilbert matrix and using format wrap. So because when you display the matrix in other formats, it's difficult to see what the formula would be. But if you display it as fractions, then you look at the pattern and use that to infer what the formula is. And some of you did do this, but enough of you did not to leave me to say something. So, and this has happened sometimes on the quizzes too. For the quizzes, these are reading quizzes. In other words, by reading a section, you'll be in good shape to answer the questions. From what I can tell, from some of the scores in the quiz, not a lot of reading was done. So something to keep in mind for future quizzes and the test, because both the midterm and the final will have questions of that type. Okay. All right. Now, next, even though I've lost some class time due to the late start, I want to talk about what's on tap for this week. So what's on the calendar for today is this section, 7.3, Newton Interpolation. And I had budgeted the whole week, both Tuesday and Thursday classes, to cover this section. Well, from looking at my notes, apparently it's not going to take that long. In fact, I'll probably finish this today, if not for all the time I spent talking about this in my late start. But we'll see how that goes. The point is, I should definitely not need the totality of what's left of this class and Thursday to cover the section. I should have a good amount of time get left over. So what I will do is this Thursday, 30th, once the section is completely covered, whether it's today or spilling over some into Thursday, I figure it's a good time to handle any homework questions that you have, or whatever assignments are out there. So if you haven't had a chance to spend time on whatever assignments you haven't already submitted, like you're working on the homework for section 2.1 or 2.2, then now's a good time to dive into those. And whatever difficulties you have, we can spend Thursday talking about that. Or related quizzes, any of that. Okay. So you can think of it as a big old office hour. Okay. Now, so we're still dealing with polynomial interpolation. So I'm going to do a quick recap of the approaches that we've seen so far. So as a reminder of the problem is we're given these points in the plane, and I need to include the assumption we're assuming that the xi's are distinct. Find a polynomial in P of x of degree.
Yes.
That agrees, that passes through those n plus 1 points. Okay. And I say at most n because some of these coefficients could turn out to be 0. It's an exceptional case, but it can happen. So approach number 1, which we didn't really spend much time on because it's not really a good approach, we substitute each of the x values into a polynomial and set them equal to the corresponding y values. That's a system of n plus 1 linear equations and n plus 1 unknowns for the coefficients that are in power form, which is how a polynomial is written in this case, and not a good approach because it's inefficient and it's not very robust either. Matrix is ill conditioned if the xi's are close together. The next approach that was better, Lagrange Interpolation. So we describe Pn of x and as a linear combination of Lagrange polynomials. The coefficients of a linear combination are easy to get, they're just the y values. And then times these Lagrange polynomials. So one drawback I was pointed out and addressed is that with the Lagrange polynomials as they're normally described, it's expensive to evaluate, but if you use barycentric interpolation, then that's a lot faster. But here's another problem I did not talk about back then. Suppose we add another interpolation point. Then all of Lagrange polynomials are affected by that. We have to recompute them entirely. We add so one whole new Lagrange polynomial will be added. The other Lagrange polynomials have to be modified. So that's expensive, and we can do better than that. So another way of describing it is this method is not a progressive method. So progressive methods are the kind where if there's more data included, that the method is easy to update. So it doesn't require reworking everything. So we'd like to have an approach that is progressive, where if you already have Pn of x, and you want Pn plus 1 of x, that there's very little work to do. And that is where Newton interpolation comes in. So now we're going to have yet another form. So here we have power form, here's Lagrange form. Now we have Newton form. So we have unknown coefficients times these polynomials. And so now I can describe those. So, as we can see, we have increasing degree. So first we have 1, then x minus x naught, and then each time through we tack on another linear factor. So in general, nj of x is a polynomial of degree j, and it starts with x minus x naught, x minus x1, all the way up to x minus x sub j minus 1. So the coefficients, C0 up to Cn, can be obtained by solving a system of linear equations in which the matrix is lower triangular. And the reason it's lower triangular is because of the increasing degree of these polynomials. And implicitly, that is what we will be doing in including these coefficients. It just won't be described that way. But having a lower triangular system is nice because the system can be solved in order n squared operations. By contrast to the first approach, using the van der Waals matrix, when we're solving for power form, that takes order n cubed operations. Okay. But here's how I can describe the coefficients of the Newton form. They're actually quite easy to get. They're called divided differences. So here's a notation for divided differences. And the way they are defined is recursively. So we use a f of a, so we're trying to approximate y equals f of x. So we can think of our y values as values of an unknown function f. So that's just to justify the notation for divided differences. So the divided differences are defined as follows. Here are the simplest ones. So f of the square bracket of xj is just the function value of xj, and in this case, that would simply be the y value at xj. Then, describe a divided difference using 2 points. So this is called a first order divided difference, whereas this would be 0th order. So that's a difference quotient. So this is actually an approximate derivative. So it's the value of f at the 2 points subtracted divided by the difference in the x values. And then higher order divided differences have a similar form. Here again we have a difference quotient. So here this second order divided difference is obtained by subtracting 2 first order divided differences. Notice in this one, the first point, xj, is left out. In this one, the last point, xj plus 2, is left out. And those are the values that are subtracted below. So then, this process continues to recursively define higher order divided differences. And actually, each of these are, yes?
Hey, teacher post.
Oh, yes, yeah, she told me. Okay. Thank you. In fact, each of these higher order divided differences is related to a higher order derivative of f. So just as by the mean value theorem, this is equal to f prime at a value in between these points. So each of these is ordered equal to, like a divided difference of order j is equal to the j derivative of f at an interval containing these points divided by j factorial. So we can use this recursive definition to compute all the divided differences. And then we can substitute these into the Newton form. So this is how the interpolating polynomial is described. So we have zero order divided difference plus first order divided difference times x minus x naught, and then second order divided difference times x minus x naught, x minus x1. So we keep going to higher order divided differences with a product of more and more linear factors until we get to the last term. We have a nth order divided difference times these n linear factors, x minus x naught up to x minus xn minus 1. So x minus xn does not appear anywhere in the Newton form. I should point out that so it actually can be shown that the value of the divided difference does not depend on the order in which the points are listed. And that's easiest to see in this case right here. If I switch xj plus 1 and xj, this would be negated, but so would this. Okay. So suppose I have this polynomial already, but then I add another interpolation point, like xn plus 1, yn plus 1. What would I do? All I have to do is compute this divided difference, so one more divided difference that I can get from previous ones, and then I have this product of linear factors. In this case, there are n plus 1 of them. So I add that to this. So it's a lot less work than in the Lagrange case in terms of updating the interpolating polynomial. So now I will show you an easy way to compute divided differences. So this is something you can do like if you're working on paper, but also for writing code to compute that. Actually, I need to start this on a new page, just so you can see everything. Okay. And the easiest way to show this is with an example. So here I have my x values, and this is the same example as from last time. But my x values are minus 1, 0, 1, and 2. And then here are my y values, so 3, minus 4, 5, minus 6. So I'm going to compute a cubic interpolating polynomial that passes through these 4 points. And here is what the divided difference table looks like. So first I start with the x values. That's my first column. My next column, the corresponding y values. So these are the zero order divided differences. And then, to fill in my next column, my first order divided differences, here's what I do. I subtract these values, so minus 4, minus 3, so minus 7, divided by the difference of these x values. So I have that. And then I do the same, subtract these, divided by the difference between these to get this. And then subtract these, divided by the difference of these to get this. So now I have my first order divided differences. And I've labeled them according to which points are involved. Are there any questions up to this point before I continue with the rest of the table? Now when I move to the next column, that process continues. So here I subtract 9 minus 1 minus 7, so that's 16. But then I have to be careful about what I subtract in the denominator. So here we have divide difference for points x0, x1, x2. So it's x2 minus x0. So think of it this way. This is the divided difference I want, and it involves this whole portion of the table. So it's the x values at the extremes. Those are the ones I subtract. So 1 minus 1 minus 1. So I get 16 divided by 2 to get 8. And then the same thing happens over here. Minus 11 minus 9, so minus 20, divided by these two x values. So to keep in mind, the points indicate which x values, the first and last, indicate which x values are to be subtracted to get your denominator in the divided difference. And finally, I subtract these two, so minus 10 minus 8, divided by the difference of the very last and very first points. And as you have that, I have that written out here. So our final divided difference is minus 6. Okay. So now that we have the divided differences, we can construct the interpolating polynomial. And there's different ways you can do it. So I'll show you two of them. So you can take the coefficients from the top row, so 3 minus 7, 8 minus 6, and watch what they're multiplied by. So 3 is just by itself, that's a constant term. Plus minus 7 times x minus x naught. And then the next term, the 8, has x minus x naught, x minus x1. And then the last divided difference of minus 6 times x minus x naught, x minus x1, x minus x2. So see how it's built up that way. Or I can use the bottom row. As long as I keep it careful about which polynomials I multiply each one of these by. So I start with the minus 6, it's a constant term. And then here, at the bottom row, I'll multiply the minus 11 by x minus x3. And so notice I go backwards through the points in this case. Like the third term, I have this divided difference, x minus x3, x minus x2. And then the last divided difference, x minus x3, 2, and 1. Now, if I were to expand out both of these, polynomial that I would get would be the same because of the uniqueness of the interpolating polynomial.
Is it always going to be unique?
Yes.
Okay, just making sure.
Yeah, and that comes from the first approach of solving a system of equations. Matrix is invertible, so
Yeah.
But can we choose other paths to add them up?
So what?
Just other paths, such as maybe, for example, f of x2, and it has 5 and 11, minus 11 and negative 10 and negative 6. Just other paths.
Yeah.
Just change the order.
Yeah. That's the best way to make sure that you get the right polynomials to multiply by.
Yes, the corresponding
yes.
x or xi.
Yeah. So for example, if I started with this one,
Yes.
then my next term would involve x minus x2,
Yes.
and so on. Yeah.
So it works.
Yeah. Okay. Now, for the next, as far as how to evaluate the Newton form once you have it, okay, so I'm going to show you, actually, I need to temporarily unshare. I need to show you something from the text. Newton interpolation. Okay. So here's the pseudocode for the algorithm for what I just showed you, filling in the divided difference table. So what this does is it creates a matrix D, where only let's see, I in this case is greater than J. So it is a greater than or equal to J. So it fills in the lower triangle of a matrix of size n plus 1 by n plus 1 that stores all the divided differences like I just showed you. And then, in this case, we're making the assumption that the top row is being used. So these are the divided differences that are returned by the algorithm in this case. And actually, I believe one of the problems I assigned from this section, yes, this problem is to write a MATLAB function that will implement that algorithm. So you give it a set of x values and y values, in other words, f values, that it will produce the divided differences. So it'll compute the whole table, but the output to be returned are just these divided differences that come from the top row. Because that would be enough to form the Newton polynomial. Now, once the polynomial is computed, this is an algorithm that can be used to efficiently evaluate the Newton form. So nested multiplication assumes that the evaluated polynomial with these given coefficients and these centers. So I'll show you intuitively how this algorithm is proceeding and why it produces the correct result. With an example. Okay, so here is the polynomial that was produced using the top row of the divided difference table. So what's done here is the polynomial is rewritten in nested form, because notice if I look at every term except the first, each of these terms has a common factor, x minus x naught. So I factor it out. Then when I look at what's left, I have this term of minus 7, but then everything after that, so in other words, these two terms, also has a common factor of x minus x1. So that gets factored out, and I keep going. So now when it's written in nested form like this, it can be evaluated with a minimum number of operations. So if I have a given x value, and I want to value P3 at that x value, then these are the steps that are actually carried out. You start from the inside and work your way out. And this is what the nested multiplication algorithm is doing. So starting with the highest order coefficient, then multiplies that by x minus x2, which is the second to last x value. Then, once these first two steps are done, this is what you have. So then you add on the next coefficient, and we're here. Then you multiply all of that by x minus x1. I'm going to rewrite this so it's more uniform. Y plus 8. Just so it's the same format as these other lines. Okay. All right. So what we do is coefficient multiplied by x factor. Add next coefficient multiplied by the next x linear factor. Add on the next coefficient multiplied by the next linear factor. Keep going until you've gone all the way through to the end. And then when you add on the 0th order coefficient, the constant term, then you're done. Now this is a third degree polynomial, and only 3 multiplications were required. So in general, for p n of x, you only need to perform n multiplications. And the Newton form lends itself naturally to this nested representation. Whereas with Lagrange, we'll see. you can try something similar with Lagrange, but the individual terms would be a lot more cumbersome because you'd have a whole polynomial, not just a constant. All right. Okay. So then, I should mention this multiplication, that's algorithm 7.3.5, yes, is a generalization of an algorithm known as Horner's method. That's for evaluating polynomials in power form. So if I have, this is an example, P3 of x, written in power form, so it should be squared, then that can be written in nested form also. Okay, so the same idea applies, is that instead of multiplying by x minus something, you're just multiplying by plain old x. So again, only 1, 2, 3 multiplications are needed. So this is how polynomial evaluation is generally implemented, as opposed to actually computing x squared, x cubed explicitly, because that would not be as efficient. Okay. Now, since there's still time, I also want to mention something else that can be done with nested multiplication. And that is, suppose you have your polynomial in Newton form like this, but you would like to convert it to power form. Then nested multiplication is serves that purpose too. And what I can do is show you an example. Okay. So here's that same interpolating polynomial. I've just filled in the x values. So what I want to do is convert this polynomial from this Newton form to power form. And the way I can do that is use nested multiplication 3 times. And 3 times because it's third degree. So what I do is, if I carry out this nested multiplication algorithm, so this is what it would look like for degree 3, and I set x equal to 0, then what that does is, when I overwrite these, so if I put in the coefficients of the original Newton form, the c's, then I compute these b's. What I get from here is a new Newton form, so with different centers. So in the Newton form, I have centers, x0, x1, x2. Now what happens is, these centers, x0, x1, x2, are changed to have 0, x0, x0, and x1. x2 gets pushed out. So watch what happens. This Newton form is now this Newton form, where the coefficients come from all the intermediate steps of nested multiplication. So now I have 0 as my first center, x0 is my second center, x1 is my third center, and x2 is out. So it's not power form, but it is progress towards power form, because I have b0 plus b1x, and then other terms. So now that I've changed one of the centers to 0, I can just do this again. Okay, so here's that process on, oh, okay. So here's that process on this polynomial carried out, and this is what it looks like. So it's closer to power 4. -1 and 0 were two of the original interpolation points, and then 0 is the center that's been added. So now I do it again. And so here's my updated Newton form that has these centers, 0, -1, 0. So I apply nested multiplication again, and my evaluation point is once again 0. Not sure why I have that z there, it should be x. Okay, so now these are the b values that are produced. I go ahead and work these out. So now I have Newton form changed again, and my centers 0, 0, -1. So this center was pushed out. This one got moved to a final position. Now I have 0 and 0. So, okay. Then I do it one more time. Again with 0 as the evaluation point. And now this center is pushed out, and all the centers are 0. When all the centers are 0, that's power form. So it's possible to write code that would just call nested multiplication n times, where n is the degree. And you're maintaining a list of centers that originally are your interpolation points, except for the last. And then you throw in a 0 and shift the last one out, and you keep doing that. And then the output of nested multiplication are the coefficients for the next time. That's actually the subject of one of the explorations. It's this one. Now, I did not assign this one because students really struggle with it.
It seems like really hard to do.
Yeah, and I got tired of grading it. So it takes as input the divided differences that are produced by the diff, a problem I did assign, and then the interpolation points, and it will convert to power form, where you'd have to write a function that carries out this algorithm and takes as input these coefficients, and x in this case would be 0, and the output would be these b's, because those are the changed Newton form coefficients. I'm open to giving bonus points if anyone wants to do it anyway. But would understand if you wanted to leave that on the table. But the problems that I did assign are okay. So this one, implementing a divide difference algorithm, and then this one that would evaluate the Newton polynomial at given x values. And this calls for implementing nested multiplication. So in fact, by doing the problems that are required, you'd be pretty well set up to do one that isn't. But I understand. It seemed like a versatile thing to do. Okay, so all right, so let's let it come here. Multiplication by n times to Newton form can convert to power form. And see, that was example 736. Oops. Looks like I had things go over to another page. Okay. All right. essentially all I have for this section. So, okay. Well, in that case, I have time to entertain any questions over about this or about homework or quizzes.
Was it through 7.4 or 7.2 that the midterm was on?
Oh, up to 7.4.
Up to 7.4.
Okay. I hope it wasn't. We didn't put out 7.2 anywhere.
You didn't. I was just looking at dates.
Oh, gotcha. Okay.
Professor, I have a question about the concept check, maybe section 2.2, maybe. It is talk about it is about underflow and overflow. So it asks about which one is more problematic. So I don't know which one will be. Yes, maybe question 3. Yes. Which one
okay.
is more problematic? I think both are bad.
Oh, I see. Okay. Well,
because if we allow some numbers to not normalize, we can even express more numbers near 0, right?
right.
Yes.
So that would forestall underflow.
Yes.
Yeah, because if you require normalization all the time, so if you did not implement gradual underflow, then the smallest number you could represent would be 2 to the minus 1022.
Yes.
Now we can go all the way to 2 to the minus 1074. So it's still some point where it's overflow. So as far as determining which is more problematic, the way to look at the question is this.
Yes, I don't know what does it mean.
Okay.
Yes.
Because when a number, when you turn to a number and you get overflow or underflow,
yes,
then you're going to store something, and that something's going to have some interpretation. And do you have? So is it possible to? Can you have something you can at least work with for subsequent computations? So if because what happens is if you're performing a large sequence of computations, and one of those computations, like an intermediate step, leads to overflow or underflow, then subsequent computations are going to pick up a value and try to work with it. And if there's nothing reasonable that you can use, then the rest of your computations are worthless. But if there is something, some sort of meaningful result that you can declare a number to be when it is overflown or underflown, then maybe your computation can continue. And yeah, so that's the thing to.
Oh, so overflow will be more problematic because in medial step, if one number is get overflow, then it get infinity, and it cannot continue the process.
Right.
Continue the computation.
Yeah.
Oh, that's the. Yes, I don't know just what that.
Okay. Yep.
Yes.
All right.
Thank you, Professor.
Yep.
And question 5, best of both worlds. I don't know whether I understand it's correct. So it is for the storage and also for in reality. So if it is for storage, we don't waste such storage or some spaces to.
Yeah.
We can store more numbers.
Yes.
And for reality, we can express more numbers near 0. So we can do some fine computation.
Right.
Okay.
Yeah. So by best of both worlds, I mean, it's impossible to. So why is it the gradual underflow essentially gives you both benefits?
Yes.
Yeah. Oh, I guess you could say that it's not. If there has to be one drawback of gradual underflow,
Subnormal number.
well, that's actually probably a good thing. A drawback could be efficiency because in terms of hardware implementation to determine how the actual bits stored in the number are to be interpreted, there's a little logic in there that's needed to check whether a number is to be considered normalized or not, because you have to examine the exponent in gradual underflow. So gradual underflow means the number is normally treated as normalized,
Yes.
unless the exponent is at the smallest allowed value, in which case it's not normalized. Because if you typically decide all numbers are normalized or all numbers are not normalized, just a blanket decision in either case, then that's a simpler implementation of your floating point hardware. But now you just thrown in an if statement. Now here's so in this case, when the exponent is that smallest value of minus 1022, that means that all the exponent bits are 0 except for one of them is equal to 1.
Yes.
And maybe that's easier to check, but there's some logic involved anyway, because you're already checking that number for other things. Like, what if the exponent is set to like the highest allowed value, and that is interpreted as infinity or minus infinity or not a number. So there's already some checking going on. But that's something that they think about is, okay, we want to try to ensure meaningful results when possible for floating point operations, and store as many numbers as possible and so forth, but also efficiency in terms of interpreting the bits and then taking the proper action. Because that could be a serious drag on performance otherwise. And I'm sure that it's pretty difficult for people at IEEE to come up with a standard that meets all the criteria in terms of and efficiency being one of those things. So, and it wouldn't surprise me, I don't know, but I bet there might have been a debate as to whether to allow gradual underflow or not. Some might have wanted to simply say all numbers are normalized, because that would be more efficient.
But actually introduce the gradual, subnormal numbers.
Yeah.
Yes. So it seems that it has more pros than cons to introduce such numbers.
Yeah. Okay. So yeah, it's a trade-off.
Yes, trade-off.
Okay. Other questions? I know it's getting dark around this time.
Yes.
I like it.
Yeah, well, this way soon it'll be dark when class starts.
Winter's coming.
Yeah, look forward to that. Okay, so really, so you can think of Thursday as just, it's an office hour. If you really don't have any homework questions, then you don't have to tune in. But I would still recommend it, because like if you were to watch it later, I will record it. Because if your fellow students have questions, then those might apply to you too. So I'll be here, and we'll see that. Or if you're attending virtually, go ahead and ask questions through a chat, or by yelling off.
So we won't cover section 7.4 until next.
That'll be on Tuesday.